Okay, welcome back for part two of this review for exam three. So for this part, basically, I'm going to try to go a little bit faster anyway, because we're going to go in more detail down the road in class. Granted that the review is going to be very, very short immediately before the exam. So that's why I'm actually recording this sessions and here giving you ample time so that you can prepare for your exam. Anyway, uh, problem three in here deals with the this big mass in here of 1.2 kilogram. That is, as it's shown in the picture, and a 5 gram basically bullet with an initial velocity vi, so it hits it, and then as it hits it from the bottom, it remains in the block, so it's going to be embedded in the block itself. So the total mass, of course, is going to be 1.25 kilogram plus 0.05 kilograms. So yeah, that's the final mass. Granted, a 5 gram out of 1,250 grams is negligible. It's not really the point. The point is we're trying to find the block. We know how high it's going to go. It's going to go to 22.6 centimeters. From this information, we should be able to find the initial velocity of the entire block with the embedded bullet in it. Once we find that, then that's the final velocity of a collision. So the physics in here, there are two physics in here involved. First physics is the projectile motion, and then the second physics is the collision, or at least the first one. Actually, in order of happening, is the first one is collision followed by the projectile. So let me explain. But in terms of the solving, it's going to be backward. This thing is in. So here is the situation. So the block and with the embedded bullet arises from immediately after collision to a certain height h, and that height is actually 0.22 meters. Okay, don't forget that this is in centimeters. So from this information, we should be able to find the initial velocity. Remember, we have had, so this is one of the first equations we have shown, that the final velocity minus the initial velocity is equal to 2 times the acceleration times the displacement. In this case, it's going to be the displacement is h. The a is negative g because it's rising according to inside the earth. So this is g is pulling down. So that's what g is. And the initial velocity is the velocity after collision. Okay, so this is the velocity after collision, not the velocity of the bullet. The bullet, after it hits the block, is going to lose some of that velocity and basically lose some of its momentum and impart it to the combined now system. And that is basically the one that is going to be the origins of the momentum. Anyway, and this final velocity, when it reaches that maximum height, is going to be zero. So what we have in here, we have 0 minus v naught squared is equal to negative 2 times 10. I'm going to take g to be 10 times, and actually it should tell you somewhere in here that always assume that g is 10. It's not in here, but actually in actual exams, always use g is 10 unless otherwise told. So we're going to take g10, and the displacement in this case is 0.22 meters. So obviously the negative sign and the negative sign cancel. And from here, we're going to find the velocity to be the square root of 2 times 10 times 0.22, that's 2.2. So basically, the velocity is the square root of 4.4, okay, which is slightly more than 2, okay? It doesn't matter, the numbers are at this point in here. I can try to put a calculator in here, and the calculator actually is in here. So I'm going to put 4.2, 4.4, I'm sorry, under the square root, and it's 2.01, or 2.1, I'm sorry. So that's the velocity of the entire system, okay? Namely the bullets and the block. But before the collision, the momentum was that the mass of the block, the mass of the bullet times its initial velocity plus the mass of the block times its initial velocity was at rest, so it has a zero velocity. This must be equal to m plus m as they embed to in it times the velocity v naught that we just computed. So from here, we can find the vi to be simply equal to m plus m over m times v naught, and in here m is very, very small compared to big M. So in this case, it's going to be vi is going to be equal to 1 plus 1,250 divided by 5. Okay, I converted both to grams because it doesn't matter, it's unitless number. So you can leave it in kilograms, but it's going to 0.05. It's the same math. Times the initial velocity, times the velocity of the block after the collision. So this is the collision here, the impact of the bullet into the block, and this is just a projectile or a free fall or however you want to call it, okay? Uniformly accelerated motion, decelerated motion in this case, times V naught. And V naught we found it to be 2.1, so you can finish the math in here, and you should find the velocity to be a huge number, because remember 1250 divided by 5 is a big number, okay? That's why we add to it 1, so 1250 divided by 5, so it's 250 plus 1, so what, plus 1, times 2.1 meters per second, so it's quickly 527 meters per second. So the velocity is 527 meters per second. I'm not paying too close attention here to sig figs, but you guys are hopefully that you have 3 sig figs on the problem. So this is good enough, okay? So this is 3 sig figs in the problem, 527 meters per second. So it's a bullet. It must be traveling very fast. As a matter of fact, this is a supersonic bullet with the speed of sound 343 meters per second. So this is almost twice the speed of sound. So it's a very fast bullet, but it's a tiny bullet. Anyway, so this is this problem. Okay, problem 4. Yeah, we have time for problem 4 also. So problem 4, consider basically this geometries. Determine the center of mass for the first case, figure A. Well, figure A by symmetry, and you can do whatever math you like, is going to be the center. I mean, you can assume that this is 1 by 1, 1 meter by 1 meter, and has some sort of a surface distribution sigma. So it has a mass sigma times 1 meter squared. So that's its mass, located somewhere by symmetry in the middle. Okay. So this is going to be 1/2 and 1/2, and the other one 1/2 and 1/2. So the negative 1/2 cancels that positive 1/2. Everything cancels, so that at the end the center of mass is going to be at the center. I mean, the center of mass, x center of mass, is going to be the mass of, let's put it in vector notation, the mass of each block times 1/2, 1/2 for this upper right one, the first quadrant, plus the second mass times basically 1/2, negative 1/2, because we're here, and 1/2. The whole thing is divided by 4m, by the way. So because you have 4 of this, and close the vector, plus m, the lower one is going to be negative 1/2 and negative 1/2. So the coordinates of that are negative 1/2 and negative 1/2. And finally, the last one in the fourth quadrant has a positive 1/2 and a negative 1/2. M times a positive 1/2 and negative 1/2. I mean, all of these numbers, they cancel. 1/2, negative 1/2, that's 0. Negative 1/2, positive 1/2, that's 0. Negative 1/2, negative 1/2, that's negative 1. 1/2 and 1/2, that's 1. 1 minus 1 is 0. So the coordinates everywhere is going to be 0, divided, of course, by 4m. It doesn't matter. So it's going to be the vector position for the center of mass in this case is going to be 0, 0. Here is the point. It's by symmetry, okay? Whichever way, because if you argue that the center of mass is somewhere off of the center, I can rotate it for you by 90 degrees or 180 degrees, and you wouldn't tell the difference. So the center of mass should shift to a new location. So let's say, for example, you argue somehow that the center of mass of the whole thing is here. Then in this case, I'm going to spin it twice or once, 90 degrees. So this block will spin so that it's going to be here. So, and the symmetry in this case is the shape looks the same after the transformation. So whatever happened to the shape, the center of mass should not have shifted. And the only point that does not shift is this one by symmetry. So if you rotate if you put it anywhere other than the center of mass, that point will move. And you have a perfect symmetry in this case, at least with respect to the reflection or respect to rotation of 90 degrees, okay? Or multiples of that. So the center of mass is 0, 0, whichever way you argue it, either with the math or with the symmetry, that's fine. Now here is a problem that is interesting, okay? Try to find the center of mass. Obviously, the center of mass cannot stay in 0, 0 because we remove the piece off of it, okay? And, but the center of mass then is going to be somewhere in here, okay? It's going to shift a little. So how can we make the case for it? Again, we're going to do the algebra first. For the algebra, we're going to take these 3 blocks and find their center of mass. So we have to do it both ways. So in this case, the center of mass as a vector. So I'm dividing only by 3m, not by 4m, because I only have 3 of them, and each one of them has a mass m. So the first one is still 1/2, 1/2. The second one is negative 1/2, 1/2, with an m in front of it. And the third one is m with the positive 1/2 and a negative 1/2. Okay, look what happened. Negative 1/2 cancels 1/2, so I'm left with only 1/2. And a negative 1/2 cancels another 1/2, and I'm left with only 1/2. So at the end, the m's of course cancel. At the end, I will be left with 1/3 coming from the sum of the masses, and I have 1/2 in here, and I have another 1/2 in here, or 1/6 times 1/1, basically a sixth of the way away on either side. Okay. That's one way of doing it. Another way of doing it is a very, very powerful and important step, okay? I really want you not to forget this one, because most likely I will be doing 203 next time, and that is electricity and magnetism. We will be dealing with electric field and magnetic field and how we're calculating them, depending on the distribution of charges and distribution of current densities. And you will see that if you have a missing piece of a wire or a missing piece of a chunk of material, how you're going to find basically the current, the electric fields and all of that, this technique will come in handy. So what I'm going to do now, I'm going to assume that I still have this whole thing, the 4m basically, what I know the center of mass is in the middle, okay? And I'm going to add to it another negative mass. I know it doesn't make sense, but mathematically it's going to make perfect sense, okay? So this is a math check, not a physics at all. So we're going to add a negative mass. So think of, I'm going to add a mass that is negative to cancel this mass, okay? And try to find the overall center of mass. So I have the 4m's whose center of mass is 0, 0, okay? And I have the negative m whose center of mass is in here, in the middle, okay? So it's a negative mass. I don't know what I did in here. It erased stuff on me. Why is it doing that? I think I touched this thing by mistake. Dismiss, okay. I don't know what this is doing. It's for review stuff. Anyway, so I have a negative m whose center of mass is negative 1/2 and a negative 1/2. Okay, and this two, I'm going to find the common center of mass. So what I'm going to do is, obviously, if I add all the masses, sum of all the masses, the mi's, I have 4 m's, and I am going to add to it the negative mass, so I have only 3 m masses. We're settled on that. We added a negative mass. Doesn't make sense physically, but it's mathematically it's a perfectly legitimate thing. So the center of mass in this case is going to be equal to 4m, and its coordinates are 0, 0, minus m, and its coordinates are negative 1/2 and negative 1/2, over the total mass, which is 3m. 4m minus m, that's 4m, 3m. So this one has 0 contributions anyway, it doesn't matter. That's why we did it actually, so that you don't care about it. So I have a negative times negative, it's positive. So at the end of the day, of course, the m cancels the m. This term, this is a 0 vector, so we don't care for it. So it's going to be a positive 1/3. M cancels the m of 1/2 and 1/2. Remember, the negatives cancel. And again, I find 1/6, 1/1. Okay? This trick is a very, very powerful trick, and it's useful a lot in electricity and magnetism. Okay? As a matter of fact, we're going to apply it to this problem quickly. Figure C. In figure C, I'm going to assume the whole sphere, or the whole circle, I'm sorry, is covered with mass, m. So that's the mass of the big sphere. So there is no hole in it. And I'm going to add a negative mass in the place where the hole is of mass m. So it's a negative m mass that I'm going to add in here. So think of it this way. So you have the whole thing is m, and you somehow add a negative m in here to cancel that big m, and now you have a hollow region in the side. So basically, the center for this one, it's clearly equal to, the geometry is given, negative 1/2, 0. So this one, its center of mass is negative 1/2, 0. And the center of mass of the big mass, m, is, of course, in the middle by symmetry too, because it has this circular symmetry, so it's going to be 0, 0. Okay, so we're done with that, okay? So that is good. But we need to know what's the ratio of these two masses. Remember, the mass in general is the distribution, mass distribution, in this case sigma, and I'm going to assume it's a uniform distribution. I think it says in some problem somewhere, that times the area, pi r squared. So the big area has this mass, but the second one has a negative mass, so it's a negative m, which is negative sigma times pi r squared. You can clearly see from the geometry that big R is 1 meter, okay? A disk of radius 1 meter, and the small hollow region is half a meter. So R is twice R. That's it. One of them is half a meter. So this mass in here is about 4 times this one. It's clearly, at least in magnitude. I know one of them is a negative mass. Okay? So in magnitude, this big M is equal to negative, how am I going to put it? Or let's put it, yeah, with a negative sign. Because little m is supposed to be a negative mass anyway for m. Ignore this, just leave it as is, okay? Let's not get things as complicated. So the total mass now, which is the sum of the two masses, is going to be equal to sigma times pi times r squared minus r squared. That's the bottom line, okay? And remember, r squared is twice r squared, so we're going to put it out if you want to, or you can pull the other term out, so it doesn't matter. At the end, this is equal to sigma pi times r squared times 1 minus r squared over r squared. And this number is clearly 1/4. Because remember, little r is half of big R, so 0.5 squared divided by 1, that's 0.25, okay? Remember, the units, the meter and the meter cancel. So it's 0.25, dimensionless. So at the end of the day, the sum of the mass, the total mass, that's the key for the whole problem, honestly. Total mass is going to be equal to pi r squared times sigma, that is the big mass M. That's the total mass M of the unbroken disk, times 1 minus 1/4, okay, or 3/4 of big M. Okay, that's it. So once we find the total mass, then finding the center of mass is just dividing this quantity by the total mass, which is 3m over 4. Okay. Now the magnitude of this number also, the magnitude of little m, which I can cancel the negative sign on this one in here, is going to be equal to, the magnitude of m is equal to sigma times pi times r squared. And r squared, if I divide by r squared, I multiply by big R squared. So this is just 1/4, and this is sigma pi r squared, which is big M. So big M times 1/4, quarter of the whole. In other words, this thing region in here is a quarter of the whole thing if it was filled. Of course, it's not filled. Okay. So now let's go back into the center of mass. So the center of mass, RCOM, is equal to big M, big M is not a vector, times 0, 0, which is, that is the center of mass of the whole thing, minus this M over 4, that's a little m, which is M over 4, of coordinates negative 1/2 and 0, okay? Negative 1/2 and 0, that's the center of mass, it's in here somewhere, here it is, and this is negative, so the negative times negative is going to be positive, and divided by the total mass, which is 3/4 of m. This is 0 vector anyway, so it's not going to bother us. Negative times negative is positive. M cancels the m, quarter cancels the quarter, so it's going to be 1/6 again, okay? 1/6, but 1, 0. So the center of mass is somewhere in here on the x-axis. Again, this should be also the same result if we do, this is the old problem, so that we don't confuse these two. So the center of mass is going to be on the x-axis anyway, because this is symmetrical with respect to the x, rotations around the x-axis. But there is no symmetry around the y-axis, because if you spin this, the hollow region will move to the other side. Anyway, I spent too much time on this problem. Hopefully you guys understand it. And if not, we'll have more discussions on it. And believe me, we will have more discussions on it in 203 too. But for the sake of the exam, also you need to understand how you find center of masses either way, either with the subtraction method or with the pure numbers. Okay, just find the center of mass. Okay. Here is going to be very, very hard to do the integral because you're going to integrate throughout the entire shape in here, and the boundaries of integration are going to be a nightmare. So don't even try to do the summation, basically, technique. The only way, the best way, not the only way, the fastest way and the easiest way is what I showed. Okay. Anything else will involve complicated integration, double integrals. That is, I think, for a lot of you didn't do the multivariable integrations already. So don't go there. This is easy, and that's why we use it actually. Okay. Okay. So in other words, the previous question was just training for this one. Let's see if we can get another one out of the way. Okay. 5. What is the moment of inertia, ICOM, of a propeller with 3 blades? I think this one I had a discussion with one of you the other day in the office hours, and hopefully he can help us later on during the review. Basically, at least he will do it himself. Okay, so basically you have three blades. I'm going to try to draw them as best as possible. The angle between them is 120 degrees between each two. That is just to say that the center of mass in here. So this is the center of mass where the blades meet, okay? Because if they were shaped any other way, the center of mass will shift to closer to where the distribution is. Okay, so that's where the center of mass is of the entire shape. And what is the moment of inertia? What is the moment of inertia around the 3 blades? Blades of mass m, so each and every one of them has mass m and length l relative to each other. So basically, with respect to the center of mass, so the center of mass in the middle, and it's the end of each and every one of them. Remember, we did in class the moment of inertia of a rod around the end is 1/3 of ml squared. In this case in here, I have 3 of them. So it's, well, first of all, the masses, it's a little k, lowercase m and a big case l. But I have 3 of them, and they're all in the end because that's when the center of mass of the whole thing is. So that's where the center of mass is at the end of each and every one of them by symmetry. And again, it's going to be 3 times 1/3 of ml squared. So it's simply ml squared. That's the moment of inertia for the entire propeller. If a torque tau acts on this, how long will it take for it to reach a velocity omega? Okay, remember, if a torque tau acts on this one, tau is equal to I alpha. I, we just computed it, so somehow torque has been applied to this propeller to get it going. And from here, we're going to compute I as being tau as being tau, alpha as being tau over I. So it's basically alpha is equal to tau over ml squared. Okay. And then how many? We can compute it only tau alpha. We need to find the time it takes for it to reach this speed. It started from rest, so omega naught is 0, and omega is equal to alpha t. From here, t is equal to omega over alpha, and that's going to give me ml squared omega over tau. Okay, so that is basically the time it takes for it to reach a certain speed, omega. So omega is known. The mass is known, the length of each blade is known, and the torque is known. So from here, we should be able to compute the time t. And then, where are we now? How many revolutions will it have before it would have made before reaching omega? Well, in this case, it's revolutions, by the way, not. So you have omega, okay, and tau. I mean, you can do it in 2 ways. Either theta is equal to 1/2 of alpha t squared, then you just compute a t. So you plug in that equation in there in theta. So there's going to be the number of radians, how many angles it has spun. But we want to find the number of revolutions. So theta over 2 pi. So that's the number of revolutions is equal to actually 1/2 of alpha t squared over 2 pi. Or in other words, alpha over 4 pi t squared. So we just computed alpha, we have t, so we can do it that way. Or there is another way of doing it, and that is omega squared minus omega naught squared, which is 0, by the way, is equal to 2 alpha times delta theta from here, or theta in this case. That's really what we're after. So theta in radians again. So it's going to be omega squared over 2 alpha because this number is 0. The initial angular velocity is 0. And omega squared is fixed, okay? And 2 alpha, alpha is equal to tau times, and then I have ml squared in here. That is basically alpha. So that's basically the value of tau in radians. So this is actually much easier than having to multiply t squared and multiplied by alpha. You should be able to find the same answer. So these are two ways of doing it. So the number of revolutions, again, because they want to, how many revolutions it did, is the same tau over 2 pi. So it's going to be omega squared ml squared divided by 4 pi times tau. Okay, and a bunch of Greek letters in here. You have the pi, the tau, and the omega, and the m and the l are both Latin words, Latin numbers in here. Okay. So, and now get the numerical. So now they give you L equals to 1.25 meters. M is 12 kilograms. That's a huge blade, by the way. It's a meter long. It must be heavy. Tau is 3,000 Newton meter. And omega is 2,000 radians per second. So basically, you have all of these values, you plug them in here, you have omega squared, which is 2,000 squared, times the mass, which is 12 kilogram, times L squared, which is 1.25 squared divided by 4 pi times tau, and tau is 3,000 Newton meter. So you can find the number of revolutions, basically how many rotations it did, the blade. And also you can find the time. Again, you have the mass, you have L, you have omega, you have tau. So you can find all of these quantities. Okay, hopefully you guys can have no problem with this one. I'm going to stop the recording right now, and I'm going to resume it later on. Thank you.